Morning. Pre-calculus. I need to wake myself up right now. Okay, so we're going to talk about sections 5.1 and 5.2. Let me share my screen here. Okay, so sections 5.1.1 and 5.1.2 are talking about exponential functions. So we have to remember, first of all, way back from algebra and algebra 2, that something is exponential if it's in the form y equals a times b to the x power. And a is, if you're looking at the graph, it's the y-intercept. And when you talk about y-intercept in terms of a situation, it's your initial value or your starting value. So a lot of times things that are exponential have to do with, increasing or decreasing by 1%. So the amount you start with. B is your multiplier. So when we talk about, things that are linear, we talk about y equals mx plus b, and m is the amount you increase by at a constant rate, and b is the amount you start with. And something exponential is that you're multiplying by the same amount. In division, we're going to think of as multiplying by a decimal or a fraction. So this is what we dealt with back in, like I said, algebra 1, algebra 2, but now we have also talked a lot about other transformations where we could have a horizontal transformation or we could have a vertical transformation. So we're going to add that in as we're going today. So we're going to do a few examples. Now, a lot of these you are looking at a situation, so you're going to read through and kind of try to figure out, where everything comes into play in these in the formulas, how they relate. All right, so let's look at this first one. These first few are from 5.1. All right, so Ramel has saved $4,000 and plans to invest in an account earning 5% interest compounded quarterly. Assuming no further deposits, how much money will Ramel have in the savings account after 2 years? Okay, so this talks about compounding quarterly. So let's first actually think about this. If it just said compounded yearly, if it just said compounded yearly, and then we'll talk about, well, now how does that change if it's compounded quarterly? But it might help to think of it first a little bit in a more simple situation. Okay, so if it was just compounded yearly and we're thinking about y equals a times b to the x, starts with 4,000. So that would be our a value. And then it earns 5% interest. So that means it keeps 100% of the existing interest plus an additional 5%. So that's 105%. And when we have to go from a percent to like a rate, we divide by 100. So this would be what we're going to call our R value of 1.0 or 0.5, or I shouldn't say that. So this is going to be 1.05. So our multiplier here is going to be 1.05 and then to the t power. This is if it was compounded yearly. So you might remember when you had things that were increasing or decreasing by a percentage, that we would tweak this formula here to be a times 1 plus r. And that r is where you take your percent and you divide by 100. And then to the t power. Now, if you're increasing by a percent, it would be plus r. Like here, we were increasing by 5%. If we were decreasing by a percentage, it would be minus. So it's adding or subtracting depending on if you're increasing or decreasing. For example, cars tend to depreciate in value. That means they decrease in value by a percentage. So if a car depreciated by, let's say, 10%, we would say, okay, well, 1 minus 10% would be 0.1. So then the multiplier would be 0.9. So thinking, okay, it was worth 100% of its value. We lost 10% of its value. It's now worth 90% of its value. We're going to divide by 100, and that's going to give us 9.90. That would be our multiplier. Okay, but this situation says not that it compounds yearly, but it actually compounds quarterly. Okay, so the way interest works is if it's compounded quarterly, first of all, they take the 5% and they split it by 4 because they're splitting it over 4 sections. And then the other thing that happens is it gets compounded 4 times a year, not just once a year. So this formula here is going to change a little bit. So when we're just talking about, before we do compounded quarterly, let's do this. Just say, we're going to just say compound interest in general. The way we're going to tweak this formula is we'll still have the A, and then we'll have 1. It's always at your earning interest, so plus. And because that rate is going to be split based on how many times the interest is compounded, in this case it's 4, but it could say it's compounded monthly or daily or weekly, right? So I'm going to say N, and N is going to be the number of compoundings per year. So for example, N equals 4 would be quarterly, okay? If it was monthly, it would be 12. Monthly, I can spell, okay? If it was weekly, it would be 52, and so on. All right, so that's what would be inside the parentheses. So this is changing to R over N. But then if I just put T here, it means it's being calculated just once a year, like here. But in this case, it would be calculated 4 times a year. So we would do 4 times T. In general, it would be N times T. So this is our formula for compound interest just in general. So then when we think about this situation here, we would want to start with what, 4,000. So Y equals 4,000. And then we'd have 1 plus, now the rate is 5%, so we would use 0.05 divided by 4 to the 4 times T power. All right, so then we can clean this up a little bit, right? So we can figure out what 1 plus 0.05 divided by 4 is. So that would be 4,000, and then that comes out to be 1.0125 to the 4T power. So then if I wanted to know the interest at the end of a certain number of years, then I would put that number of years in here. So this would be my formula for that situation. All right, so let's take a look at this next one. So this next one talks about atmospheric pressure. Is the pressure exerted by the weight of air in the atmosphere of Earth is caused by the weight of air above the measurement point. As elevation increases, there is less overlying atmospheric mass, so that atmospheric mass decreases with increasing elevation. At sea level, at 0 feet, so like when they tell you that, sometimes I'll even make a little table, right? At 0 feet, the atmospheric pressure is 101 kilopascals. For every 500 feet, so then after 500 feet, it decreases, right? So it decreases by 1.8%. What is the atmospheric pressure at X feet? So every 500 feet, we're seeing this decrease of 1.8%. But I don't want to know after 500 feet. I just want to know after X feet. So when we go to write our formula, now this doesn't have to do with compounding. I'm not going to use this compounding formula. I'm going to go to this one here. Okay, so I'm going to use that idea here. And because it's decreasing, right, it's decreasing by 1.8%, I'm going to use the idea of A times 1 minus R to the T power. So I'm starting at 101 kilopascals, and it's decreasing by 1.8%. So my R value is when I take my percent and I divide by 100. So if I take 1.8 and I divide by 100, that moves my decimal place back 2, so that's 0.018. So here I have 0.018. And now, before I talk about my T here, I'm going to subtract this. So 0.982. So if I lose 1.8%, I'm keeping 98.2%. Now, I'm not going to just do this to the T power, because if I do that to the T power, that means this is happening after every 1 foot, right? But this happens every 500 feet. So like if I wanted to figure this out after 1,000, I'd have to actually take 1,000 and divide by 2. It's like how many sets of 500 are there? Because I only want to know after 1 foot. So then what I would have to do to this is I would have to then divide by 500. So it really does relate back to what we did in algebra, like the a times b to the x, but they're a little bit more, nuanced. There are other things that you have to consider. It's not just after 1 year, right? This happens every 500 feet, and this is x. I don't know why I use t. It's every 500 feet is the pattern is happening. So I would have to divide by 500 to figure it out after just 1 foot. All right. And then the other thing that you can do, and we'll get more into this as we go throughout the chapter, is sometimes you're going to be asked to rewrite your formula so you just have a single variable up here instead of having this division. And so something that we're going to talk about as we go throughout the chapter, and we'll see this when we moved into 512, is that this right here can be split into 1 over 500 and then to the x power. So I can do 0.982 to the 1/500th to the x, because remember, power to a power you multiply. And then what you can do is that you can put this into your calculator and get like whatever that digit is, and then have it simply to the x power. So that's something that we're going to move into as we go throughout this process. All right, let's look at another one of these. So part C says a scientist grows bacteria starting with a culture of 5 bacteria. Bacteria grow by multiplying. After 2 hours, there are 14 bacteria. How many bacteria will be present after T hours? All right, so if this is like our time here, and then this is like the number of bacteria, then I know when I start, there are 5, and then after 2 hours, there are 14. I'm going to leave a little space there because it's like I want the multiplier, but I don't know, like there's something going on here in between. So we can start with this y equals a times b to the x. And I know that a is 5. And then what I could do is I could use this 2 and 14 and plug 14 for y and plug 2 for x, and then get my b value. So it's sort of like when you would write an equation for a line, like how first you would find the slope, and then you would have to use the y equals mx plus b to get the y-intercept. It's sort of the same idea, but now we're using this. So to get my b, I would have to take the square root of both sides, or think of it as the 1/2 power. So b equals the square root of 14/5, which is the same thing as 14/5 to the 1/2 power. So when I go to write my equation, I would say y equals, my a value was 5 times 14/5 to the 1/2, and then to the x power. So then I could write 5 times 14/5 to that, if I multiply these together, and that could be a t also, right? That would be the t over 2 power. All right, one more here. All right, Julie has a fresh cup of coffee. So all these ones we've talked about so far haven't had any sort of shift in it. So now we're going to see one with a shift in it. Julie has a fresh cup of hot coffee that has a temperature of 180 degrees. The temperature of the room is 70 degrees. Sketch a graph of the temperature of coffee over time, and then let T equal the minutes and Y equal the temperature. So this is temperature and this is time. 5 minutes after Julie pours her cup of coffee, it's 160 degrees. Write an equation to model the situation. So after 0 degrees, it's 0 minutes. After 0 minutes, the temperature is 180 degrees. But then after 5 minutes, it's 160 degrees. Okay, so if we think about the graph and you think about a cup of coffee cooling, the temperature is going to decrease, but it's not going to go down forever. If room temperature is 70 degrees, if this is 70 degrees, it's going to decrease, but it's going to level off at 70 degrees. Okay, so it's something exponential. So we know it's of the form y equals a times b to the x, but there's a vertical shift of 70. That means you have a k value of 70. So we would have a plus 70 here. Okay, and then we know at time 0, the temperature is 180 degrees. So we can't just throw the 180 here for A because of this vertical shift. It's not quite that simple. But I do know the temperature, so that's my Y value, is 180 degrees when the time is 0. So when you look at this, you could now solve this equation and figure, well, you figure A out, because B to the 0 is just 1. Okay, so that means 180 equals A plus 70. So A is 110 degrees. Okay, so now I can refine this equation a little bit. I have Y equals 110 times B to the X plus 70. But I need to know the B value. So now I'm going to use this point, and I'm going to put the 160 in for Y, and I'm going to put the 5 in for X, and I'm going to solve to get my B value. So the first thing I would do is I would subtract the 70. So I'd have 90 equals 110 times B to the 5th. And then I divide by 110. So I'd have 90 over 110 equals B to the 5th. Okay, and then I can reduce the 90 over 110 to just 9 over 11. But to undo the 5th power, I'm going to take the 5th root, or I could do the 1/5 power to both sides. Okay, so the 5th root is the same as the 1/5 power. So now going back up here, I can refine it further because now I also know the B value. So now here I have this B value, and can go here in place of the B. So my equation will be Y equals 110 times 9/11 to the 1/5 to the T power plus 70. And so then I'd have Y equals 110 to the, I could write this as 9/11 to then when I multiply these together, that's T over 5 power plus 70. Okay, so the first section is really just practicing reading those situations and trying to pick out A's and B's, like what's your start, do you have vertical shift, and so on. Okay, so when we get into 512, now we're going to talk about stretching exponential functions and whether or not it's possible to have equivalent transformations. So when we've talked about transformations before, we've had this formula, right? And it's still that, you know, A is vertical stretch and B is horizontal, and this is a horizontal shift and this is a vertical shift. And what we're going to investigate today is it possible for like one of these transformations to be equivalent to the another transformation, like stretching a certain way being equal to shifting a certain way? So we're going to be investigating, can two different transformations give the same result? So to explore this, we're going to be practicing a little bit with using some exponent properties. In particular, the fact that if you have two things with the same base, you add the exponents. Right? So if I have the same base, I would add the exponents. If these are the same numerical base, I would still add the exponents. Okay, the other property we need is power to a power. So if I have a power to a power, I multiply the exponents. And I was using that one a little bit when I was doing those other problems. So if I have, I want this to be a number, I think actually. So if I had 2 to the x to the 5th, that's 2 to the 5x. And then if I had 2 to the 5x, I could bring it back to this. All right, or I could take this right here and I could split it different ways. Okay, so we're going to be using those ideas here. So it says, consider the exponential equation k to the x equals 5 times 2 to the 3rd, and then that whole thing is to the 3 times x to the negative 2 power. Can this equation also be written just to the form y equals a times b to the x? So like I mentioned a minute ago, when we had the one, like if I want to rewrite it with just a single, I just want it so I have the power of x. I don't want all of this stuff here. So that's what we're going to think about right now. So can we rewrite it with only having a vertical stretch? So right now, this has a vertical shift or a stretch of 5. And then here there's a horizontal stretch going on. And then here we have a horizontal shift to the right. So the question is, can I rewrite it in this form so there's no longer a stretch, or a shift rather, only a vertical stretch? So we're going to use properties of exponents to try to rewrite this. All right, so the first thing that I see here is I could think of this as 5 times this 2 to the third to the x minus 2. Like I could think of this there, it is being a parenthesis here, right? I could first say 2 to the third is 8, and then I have to the x minus 2 power. Now over here, when I had this 2 to the x plus times, 2 to the 7th, I rewrote it as 2 to the x plus 7, right? I took these two things and I added them together, kept the base the same. I could also go the other way. So if I had 2 to the x plus 7, that means I must have been multiplying two things with the same base. And then here, those exponents would be separate. So I'm going to use that idea here with this 8 to the x minus 2. This would be the same thing as 8 to the x times 8 to the negative second. Okay, so take a look at that and make sure that really makes sense. Because if you think about it, if you have, these are the same base, I could add the exponents, which would give me a single base with the exponents added, it would give me this. Okay, so that's equivalent, you can do that. And I'm going to rearrange this a little bit. 8 to the negative second, that's just a number, that's just 1 over 8 to the positive second, and then times 8 to the x. And so then I have k to the x equals, this is 64, so this is 5 over 64 times 8 to the x. So the question had been, can I take this and rewrite it in this form? And that's what I've done. Here's my a, and here's my b to the x power. So I can rewrite something with a horizontal shift to just have instead a single vertical shift. And that is what we're trying to get at today. Is that possible? All right, so we're going to take a look at this next one. And we kind of want to see, well, why does that work? How does that look graphically? All right, so it says in working with exponential functions, it's not surprising that properties of exponents are needed. So it says consider the function f of x equals 3 to the x. It says sketch a graph of this function. All right, so I have it here in decimals. We're going to just take a quick look at it. There it is. That's what it looks like. Okay, it's exponential growth. So sketch it. It says write an explicit equation for and sketch the graph of f of x. So it says g of x equals f of x plus 2. Okay, so g of x equals f of x plus 2. Okay, so we have this, and then we have a rule up here called f of x. So when it says f of x plus 2, that means substitute x plus 2 into the f rule for x. Okay, so g of x then would be 3 to the x plus 2 power. And it says, okay, graph that. All right, so I'm going to graph it in decimals. So y equals 3 to the x plus 2 power. And we can see, all right, it's just the parent function, but it got shifted up 2. It's got a horizontal asymptote at 2 instead of at 3. Okay, so that's what has happened to that one. Okay, so this is a, wait, hang on, I put it in wrong. Shoot. It shouldn't be going up 2, should it? It should be going left 2. Was anybody screaming that at the screen? Look at what happened when I typed it in. When you do this, this is a good lesson. When you go to put these in decimals, you have to put your exponent in parentheses. Otherwise, it just bumps it down. Okay, there we go, left 2. I was looking at that equation saying, wait, that wasn't right. Okay, so it went to the left. So it shifted left 2 units. All right, now write an explicit equation and sketch the graph of h of x equals 9 times f of x. So that means that I'm just going to have 9 times, well, f of x was 3 to the x, so 9 times 3 to the x. Okay, so now I'm going to type in y equals 9 times 3 to the x. And, all right, so here I have it typed in. So here is what I had before. That's the blue graph. Now watch when I turn this one on. Do you see it's right there on top of the other? So those transformations, the transformation of shifting to the left 2 is the same as a vertical stretch of 9. Okay, so what do we notice about the graphs? They end up being the same thing. So it's possible for a horizontal shift to be the same as a vertical stretch. Okay, so now we're going to practice using properties of exponents to show why that works. So here it's saying if I have this function here, that f of x plus 2, so a shift of 2 to the left, is the same as a vertical stretch of 16. Okay, this one is saying if I shift to the right one, it's the same as a vertical stretch, well, really a compression of a quarter. All right, so we're going to show that these are the same algebraically. So we're going to do some algebraic manipulations to show that these are equivalent. All right, so for this one, when it says f of x plus 2, that means in my f rule, in place of the x, so here in place of the x, I'm going to put in x plus 2. And I'm trying to show that it equals 16 times f of x. So 16 times 3 times 4 to the x. So I'm trying to prove that these are equivalent, right? So over here, I mean, I just see this as, it's just 48 times 4 to the x. We'll leave that alone. Now this here, this 4 to the x plus 2, I can split up into 4 to the x times 4 to the second, right? Because if I have two things with the same base and I can add them and keep the base. So these two things are equivalent. Okay, I'm going to flip-flop, or I'm going to multiply now these together. So 4 to the second is 16. So I have 3 times 16 times 4 to the x. 3 times 16 is 48 times 4 to the x. You see that's the same thing as what we had on the other side. Okay, so we're trying to show that they're equivalent, and here I've done it. Okay, same idea with this one. When it says f of x minus 1, in place of the x, so I'm going to have 3 times 4 to the x minus 1 equals 1/4 times my f of x, which was 3 times 4 to the x. Okay, over here, I can just multiply these constants together. So 3/4 times 4 to the x. And then over here, I'm going to split this, right? So instead of 4 to the x minus 1, I'm going to think of it as 4 to the x times 4 to the negative 1 power. So then I would have 3 times 4 to the negative first means 1/4. And I'm just reordering things so that I have my constants next to each other. And then that's 3/4 times 4 to the x equals 3/4 times 4 to the x. So I've shown that they're equivalent. So the big takeaway here is, in addition to being able to do these just manipulations with the exponents, which is important to be able to be flexible with them, is here. For an exponential function, a horizontal shift is equivalent to a vertical stretch. Okay, so here's how you can visualize this, because we saw that happen in the graphs. This is a typical increasing exponential function. When you look at these, if you were to stretch vertically, the same thing happens as if you shift horizontally. It just ends up having that same impact on the original. And so those end up being equivalent transformations, which we haven't seen that before, right? There's a difference between, like, if you're graphing something in trig, having like a period change and moving something left to right. Those would not give you the same graph. But in exponential, it just works out that that is how it works because of the nature of the function. All right, that wraps up 511 and 512. Take care, pre-calc students.